So far, we've spent considerable time discussing construct validity. Throughout the discussion, one question kept appearing. Did we measure the right construct? We learned that if our measurement instrument fails to represent the concept we intend to study, our findings become questionable, even before we analyze the data. Now, let's imagine that we've solved all those problems. Suppose we have an excellent questionnaire. We've learned or we've clearly defined the construct. We've used a validated instrument. We've pilot tested it. We've trained our data collectors. Everything about measurement process is excellent. Does that automatically mean our study is valid? No, the answer is still no. Because, after collecting data, another equally important question arises. Do the data justify the conclusions? That question introduces us to our second major type of validity, which is statistical conclusion validity. Statistical conclusion validity concerns whether the statistical analysis accurately support the conclusions we draw from our data. Notice that the focus has changed. Construct validity focuses on measurement. Statistical conclusion validity focuses on analysis. In simple terms, construct validity asks, did we measure the correct thing? Statistical conclusion validity asks, did we analyze those measurements correctly? Both are essential. Even perfect measurements can produce incorrect conclusions if researchers misuse statistics. So I want everyone to remember this sentence because it summarizes today's second topic. Do the data justify the conclusions? Every time you read a research article, ask yourself this question. Suppose a researcher concludes that a new nursing intervention significantly improves patient outcomes. Now, immediately ask, were the appropriate statistical tests used? Was the sample size sufficient? Were the assumptions of the statistical test satisfied? Were the results interpreted correctly? If the answer to any of these questions is no, then the conclusions may not be trustworthy. Statistical conclusion validity is really about making correct statistical inferences. Think of statistics as a tool for making decisions. We collect data from a sample, then we use statistical methods to estimate what is happening in the larger population. Our goal is to determine whether the relationships we observe are real or simply due to random chance. So, good statistical analysis helps us to distinguish genuine effects from coincidence. That's why statistical conclusion validity strengthens the credibility and reliability of research findings. Now, let's look at the nursing example. A researcher evaluates the effectiveness of a relaxation program for anxiety among nursing students. The researcher obtains a p-value of 0.03. At first glance, that appears statistically significant because it's less than 0.05. But here's the important question. How was that p-value obtained? Suppose the researcher used the correct statistical test, for example, a paired t-test after verifying that the assumptions were met. In that case, concluding that anxiety significantly decreased would be appropriate. Now, consider another situation. The researcher analyzes exactly the same data, but uses an inappropriate statistical test. Perhaps the data are not normally distributed, yet the researcher still applies a parametric t-test without checking assumptions. The p-value might still be 0.03, but now the conclusion becomes questionable because the statistical procedure itself was inappropriate. Notice something important. The numbers didn't change, only the statistical procedure changed. Yet, the validity of the conclusion changed completely. That is the essence of statistical conclusion validity. It isn't about obtaining significant results, it's about obtaining trustworthy results. Now, just as construct validity has specific threats, statistical conclusion validity also has several common threats. Some of these may already sound familiar. For example, small samples may produce insufficient statistical power, or using inappropriate statistical tests can generate misleading conclusions, or running many statistical tests increases the likelihood of false positive findings. Researchers may also misinterpret statistically significant results as being clinically important, even when the actual effect is very small. So we'll examine each of these threats individually over the next several slides. Now, look at the lower right section of this slide. So, how can researchers improve statistical conclusion validity? Okay. So how can researchers improve this statistical conclusion validity? Several good practices help ensure that statistical conclusions are sound. First, choose statistical tests that match your research question, study design, and level of measurement. Always verify the assumptions of the statistical tests before performing the analysis. Ensure that your study has an adequate sample size and sufficient statistical power. And then the next thing is you report not only the p-values, but also effect sizes and confidence intervals. Consult statisticians whenever your study design becomes more complex, and notice that statistical validity begins long before SPSS or JASP is open. It begins during research planning. So I'd like you to use a simple clinical analogy. Imagine you're measuring a patient's blood pressure. Construct validity asks, is the sphygmomanometer calibrated correctly? Statistical conclusion validity asks, did the physician interpret the blood pressure correctly? Now, suppose the blood pressure is measured accurately at 180 over 110 millimeter mercury, but the physician mistakenly records it as normal. The measurement was correct, the interpretation was wrong. So research works exactly the same way. We need to we need both accurate measurement and accurate interpretation. So I've reviewed hundreds of undergraduate and graduate theses over the years, and one of the most common mistakes I encounter is this. Students become so excited when they obtain a p-value of less than 0.05 that they immediately conclude, okay, our intervention works. Okay, but that significant p-value or statistically significant p-value is only one piece of the evidence. As researchers, we must also ask, was the sample size adequate? Were the assumptions satisfied? Is the effect size meaningful? Or is the finding clinically important? Does it agree with previous research? Now, good researchers never rely on the p-value alone. Now, I'd like you to think about this scenario. Suppose two studies evaluate the same nursing intervention. Both report a p-value of 0.03, and would you automatically conclude that both studies are equally credible? No, not necessarily. Okay? One study may have used the correct statistical procedures, while the other violated several assumptions. Now, this is why understanding statistical conclusion validity is so important. Now, I'd like to end this slide with one important message. Notice that the sequence shown at the bottom, uh, we begin with an accurate data collection. That data undergo appropriate statistical analysis. Appropriate analysis leads to justified conclusions. Justified conclusions produce valid and reliable research findings, and those findings ultimately improve evidence-based nursing practice. Every step depends on one before it. So a mistake during statistical analysis can, compromise the entire chain. Okay, so now that we've defined statistical conclusion validity and understand why it matters, our next question becomes, what are the most common mistakes that the researchers make when analyzing data? So just as we examined the 10 threats to construct validity, we will now explore the major threats to statistical conclusion validity. These threats explain why researchers may arrive at incorrect conclusions, even when they have collected high quality data using well-validated instruments. Okay. So the first threat is the low statistical power. Now that we understand statistical conclusion validity, what statistical conclusion validity is and why it is important, let's examine the specific factors. We'll begin with this, uh, which is one of the most common and one of the most overlooked threats in nursing research: low statistical power. Many studies conclude that an intervention has no effect when, in reality, the intervention may actually work. So the problem is not always the intervention itself. It may simply be that the study lacked a sufficient statistical power to detect the effect. Statistical power refers to the probability that a statistical test will correctly detect a true effect when that effect actually exists. So simply put, statistical power answers this question. If there is truly a difference between groups, how likely is my study to detect it? How likely will my study be able to detect it? A study with high statistical power has a good chance of identifying a real treatment effect. So a study with low statistical power, however, may completely miss that effect. Now imagine you're trying to hear someone whisper across a a crowded room. If the room is quiet, you'll probably hear the whisper. But if the room is filled with noise, people talking and loud music, you might conclude that no one is speaking, even though someone actually is. Now that is exactly what low statistical power does. Now, the true effect is there. The study simply cannot detect it. Okay, so looking at the left side of the slide, we see that low statistical power is usually caused by several factors. The first and probably the most common is a small sample size. Okay, when we recruit only a few participants, we simply don't have enough information to distinguish real treatment effects from normal random variation. So second is large variability among participants. When participants differ greatly from one another, it becomes much harder to detect the true effect of the intervention. So finally, the intervention itself may produce only a small effect size. So some nursing interventions create gradual improvements rather than dramatic changes. Now, detecting these small improvements requires a larger sample size. Detecting these small improvements require a larger sample size. So let's take a look at the example shown in the middle of the slide. Suppose we compare two pain management interventions. One group receives intervention A, and the other group receives intervention B. Each group has 12 patients. Now, after analyzing the data, we obtain a p-value greater than 0.05. Now, at first glance, we might conclude there is no statistical difference between the interventions. But is that conclusion necessarily correct? Well, not necessarily. Perhaps the intervention truly works. Perhaps the sample was simply too small to detect the difference. So in this situation, the study commits what we call a type 2 error. Okay, so remember the two kinds of statistical errors. A type 1 error is detecting an effect that does not actually exist, a false positive finding, while a type 2 error is failing to detect an effect that really does exist, so a false negative finding. So low statistical power primarily increases the risk of type 2 error represented by the Greek letter beta. In other words, the intervention works, but the study fails to detect it. This is why low statistical power is such an important threat, such an important issue. Okay. Now let's examine the illustration at the bottom of the slide. The graph on the left represents a study with low power, perhaps only 30%. Notice how the two distributions overlap considerably. This large overlap means the statistical test has no difficulty distinguishing one group from the other. So as a result, the probability of missing a true effect becomes very high. So compare that with the graph on the right. See this graph on the right. Now, here the study has approximately 80 to 90% power, which is generally, recommended in, you know, um, health research. So notice that the overlap is much smaller. The statistical test now has a much better chance of detecting the true treatment effect. So how do researchers prevent low statistical power? There are several important strategies. First, you have to perform an a priori power analysis before collecting data. This helps determine how many participants are needed. Second, recruit an adequate sample size. And then, of course, reduce unnecessary variability by standardizing procedures and using reliable measurement tools. And finally, select outcome measures that are sensitive enough to detect meaningful clinical change. Now, this issue is especially important in nursing research because imagine testing a new educational program for diabetes self-management. Now, if the study includes only 20 patients, the program may genuinely improve self-care. However, because the study lacks power, the results appear non-significant. So the intervention may then be abandoned, not because it doesn't work, but because this study was incapable of demonstrating its effectiveness. This could delay the adoption of beneficial nursing practices. So, I'd like to ask everyone a question. Suppose two studies evaluate exactly the same intervention. One includes 25 participants, the other includes 250 participants. Now, which study is more likely to detect a true effect? Now, exactly, of course, the study with the 250 participants, not because bigger is always better, but because larger sample sizes generally they provide greater statistical power. Now, the most important message from this slide is no, a non-significant result does not always mean that no effect exists. Sometimes the study simply lacked enough power to detect the effect. Now, whenever you encounter a study reporting no significant findings, always ask yourself, was the study adequately powered? Okay, so now suppose we have recruited enough participants and our study has adequate statistical power. Does that automatically mean our statistical results are trustworthy? Mm, Not yet. Even a large, well-powered study can, produce misleading results if the assumptions underlying the statistical test are violated. So that brings us now to our next threat to statistical conclusion validity: violated statistical assumptions. Okay, excellent. So we will continue following um, the threats that's listed here. Okay, violated statistical assumptions. Okay, so this previously we learned that a study needs adequate statistical power to detect true effect. However, having a large sample size alone is not enough. So even a well-powered study can, produce incorrect conclusions if we use a statistical test whose assumptions are not satisfied. So our second threat is this one, violated statistical assumption. So every statistical test is built on a set of assumptions. Think of these assumptions as the foundation of a building. If the foundation is solid, the building remains stable. But if the foundation is weak or cracked, the entire structure becomes unreliable. So, similarly, if the assumptions of a statistical test are violated, the resulting p-values, confidence intervals, and conclusions may no longer be, trustworthy. So statistical assumptions are the conditions that must be satisfied before a statistical test can produce valid results. Now, different statistical tests have different assumptions. So ignoring these assumptions, can produce misleading p-values, incorrect estimates, and ultimately, invalid conclusions. So Let's look at the assumptions illustrated at the center of this slide using independent samples t-test. There are three major assumptions. The first is normality. This means that the outcome variable should be approximately normally distributed within each group. The familiar bell-shaped curve is what we typically expect. The second assumption is independence of observations. So that means that each participant's score should be independent of every other participant's score. Now, one participant's response should not influence another participant's response. That is independence of observation. So you have to look at that assumption as well, or test that assumption as well, satisfy that. The third assumption is homogeneity of variance. So sometimes it's also called equal variances. This means that the variability in one group should be approximately equal to the variability in the other group. Um, these assumptions are not limited to t-tests, of course. No, other statistical tests also need to have their own statistical assumptions that you need to satisfy. ANOVA, for instance, assumes normality, independence, and equal variances. Chi-square tests assume independence and adequate expected cell frequencies. Linear regression, for instance, assumes linearity, homoscedasticity, independence of residuals, and normally distributed residuals. While, for instance, repeated measures ANOVA introduces another assumption called sphericity. The important point is that every statistical test has assumptions, and the researchers are, you are responsible for checking them before interpreting the results. So if you need to satisfy the assumptions first for you to use the statistical test. Okay, now let's consider the nursing example shown on the slide. Suppose a researcher compares stress scores between day shift nurses and night shift nurses. The researcher uses an independent samples t-test. Now, at first glance, this seems appropriate. Okay, however, after examining the data, the researcher notices two problems. First, the stress scores of the night shift nurses are highly skewed. Second, the variability of the test scores or the stress scores differs substantially between the two groups. Now, because these assumptions are violated, the reported p-value, for example, p of equal to 0.04 may not actually represent the true relationship. So the apparent statistical significance may actually be misleading. So why does these violations matter? Why are these assumptions so important? When assumptions are violated, the mathematical formulas behind the statistical test no longer behave as intended. So as a result, the probability of making a type 1 error may increase, or the study may lose statistical power, or both. In either case, our conclusions become less reliable. So let's take a look at the illustrations at the center of the slide. Now, this graph shows a normal distribution. Instead of the familiar, no, the first graph shows a non-normal distribution. So instead of a familiar bell shape, the data are heavily skewed. The data, as you can see, they are heavily skewed. Notice the second illustration shows unequal variances. Okay. Notice how one group has much greater spread than the other. And the third illustration now shows dependent observation. So for example, measuring the same participants multiple times, but analyzing the data as though each observation were independent. Okay, so each of these situations violates an assumption of the independent t-test. No, no, and there is no need for us to use or we should not use the independent t-test. Now, how do we prevent this threat? What should researchers do? First, understand the assumptions before selecting a statistical test. So, this is the first thing. What are the assumptions? Before I use t-test or before I use ANOVA in this case, for instance. And second, always explore the data using descriptive statistics and visualization, such as graphs, such as histograms, box plots, and QQ plots. And third, formally test assumptions when appropriate. So for example, you can use the Shapiro-Wilk test to assess normality, or the Levin's test to test for equality of variances. If assumptions are violated, researchers should choose an alternative statistical methods. You may not be able to use parametric tests, for instance, if these are violated. So, for example, you instead of the independent t-test, they might, researchers might use the Mann-Whitney U test or the Welsh test, Welsh t-test when, variances are unequal. So researchers should report how assumptions are checked and explain any adjustments that were made. And then, you know, consider now a study evaluating stress levels among intensive care nurses. Suppose a stress score are highly skewed because a few nurses experience extremely high stress. If the researcher ignores this violation and simply performs a t-test, the conclusion may either exaggerate or underestimate the true difference. This could influence hospital policy or intervention decisions based on inaccurate evidence. So now, let me ask you a question. Is your statistical software if your statistical software automatically gives you a p-value, can you immediately trust that result? That's a common problem. If one can do the computation using a statistical software and gives you the p-value, uh, you cannot immediately trust that result. So before interpreting the p-value, you must first ask, were the assumptions of this statistical test satisfied? Okay, so the key message from this slide is that statistical tests are only as good as the assumptions behind them. Never interpret a p-value without first verifying that the assumptions have been met. Now, suppose that we have selected the correct statistical test and all of its assumptions are satisfied. Does that guarantee valid statistical conclusions? Hmm? Not necessarily. So our conclusions can still be threatened if the instrument we use to collect data is unreliable. So now this brings us to our next threat, which is this one, right? Unreliable measures. Now imagine trying to measure a patient's blood pressure using a sphygmomanometer that gives a different reading every time. A sphygmomanometer that gives a different reading every time. Now, even if the patient has not moved, the instrument produces inconsistent measurements. Would you trust the result? The answer is obvious. Okay, the principle apply this principle or the same principle applies now in research. If your instruments are unreliable, um, your statistical analysis becomes unreliable as well. So an unreliable measure is an instrument that produces inconsistent or unstable result. So instead of measuring the true value consistently, it introduces random measurement error. That additional random error increases variability in the data, making it more difficult to detect true treatment effects. So now this slide illustrates a very important chain reaction. Measurement error increases random error increases variability, greater variability reduces statistical power. Reduced statistical power makes it more difficult to detect true effects. And so even an effective intervention may appear ineffective simply because the measurement tool lacks reliability. Suppose researchers evaluate a relaxation program designed to reduce anxiety among nursing students. One group measures anxiety using the validated GAD-7 questionnaire. The other uses a newly developed questionnaire that has never been tested for reliability. Now, both groups receive exactly the same intervention. The validated instrument produces consistent scores with little random error as expected. And then you have the unvalidated instrument, which produces inconsistent responses. Now, as a result, the second study may report that the intervention had no significant effect, not because the intervention failed, but because the instrument itself failed. So notice that we now go to these scatter plots on the right side of the slide. Notice that the first graph represents a reliable instrument. The points cluster closely around the trend line, and this makes the relationship easy to detect. And now compare it with the second graph. The points are much more scattered because of increased random error. Although the underlying relationship is the same, it becomes much harder for the statistical test to identify it. This is exactly how unreliable measures reduce statistical power. Now, what are, or yes, where are the sources? Where does this random error come from? Now, several sources are shown on the slide. First, inconsistent administration. Different data collectors may ask questions differently or record responses inconsistently. Second is poorly written questionnaire items. Ambiguous wording, for instance, may confuse respondents. Third is instruments that have never been validated. So without reliability testing, we cannot know whether they consistently measure the construct. And finally, respondent factors such as fatigue, misunderstanding, lack of attention, or mood changes can also produce inconsistent responses. So the consequences are when measurements are unreliable, confidence intervals become wider, effect estimates become less precise, statistical power decreases, and researchers become more likely to commit type 2 errors. So ultimately, valuable interventions may be dismissed simply because they were evaluated using poor measurement tools. Researchers now can improve reliability in several ways. Um, you use validated instruments whenever possible. You conduct pilot testing before the main study. You train, just like in construct validity, you have to train all data collectors using standardized procedures and develop detailed administration manuals, evaluate reliability statistically, for example, and then Cronbach's alpha should be used for internal consistency or be tested, computed for internal consistency. You can do test-retest reliability or inter-rater reliability when multiple observers, especially when multiple observers are involved. So when you have the same measurement tool, for instance, and you have different raters, you have to conduct inter-rater reliability to make sure that the same, they rate they score using the same instrument with consistency. They finally monitor data collection throughout the study to ensure now consistency. So, in nursing research, we often measure abstract concepts such as stress, resilience, burnout, quality of life, fatigue, and patient satisfaction. Uh, but unlike blood pressure or body temperature, these constructs cannot be, measured directly. So because of this, the quality of our instruments becomes, critically important. So a reliable instrument provides confidence that the changes in scores reflect real changes in participants and not random measurement error, not error due to random measurement brought about by unreliable um, tools. I suppose two researchers evaluate burnout using different questionnaires. One questionnaire has a Cronbach's alpha of 0.95. The other has an alpha of 0.52. Which study would you trust more? The answer is obvious. No, you trust the first one, which has a Cronbach's alpha of 0.95. Now, higher reliability means less random error and more trustworthy statistical conclusions. Now, the essential lesson is, reliable measurement reduces random error, increases statistical power, and produce more trustworthy research findings. So you have to evaluate the reliability of your measurements or your instruments before trusting the statistical results. Now, let's move on to the next threat. Okay, in the previous thread, we learned that unreliable measurements increase random error and reduce our ability to detect true effects. Now, let's examine a very different problem. Instead of missing a true effect, researchers may actually find an effect that does not exist. Okay, you find an effect, but actually it doesn't exist. So how does this happen? One common reason for that is performing too many statistical tests, and this threat is known as multiple testing, or what statisticians call the family-wise error rate. Multiple testing or the family-wise error rate. Now, imagine buying a lottery ticket. Your chance of winning is very small. Okay, you imagine buying 50 lottery tickets. Your chances improve not because the lottery has changed, but because you've given yourself many more opportunities to win. So the same principle applies in statistics. The more statistical tests you perform, the greater the chance that one of them will appear significant simply by random chance. So multiple testing occurs when a researcher performs many statistical tests within the same study. Now, each individual test is usually conducted at significance level of 0.05. That means that every single test has a 5% chance of producing false positive result even when no real relationship exists. When many tests are conducted, these small probabilities accumulate. So eventually, one or more tests may become statistically significant purely by chance. Now, many beginning researchers assume that a p-value of less than 0.05 always represents a true finding. That is not necessarily true. You see, a p-value that is below 0.05 simply means that the observed result would be unlikely if the null hypothesis were true. Let me repeat that. A p-value below 0.05 simply means that the observed result would be unlikely if the null hypothesis were true. So, when a however, when we conduct many tests, we repeatedly give ourselves opportunities to obtain a significant result by random chance alone. So this inflates the family-wise type 1 error rate, which is the probability of making at least one false positive conclusion across the entire collection of statistical tests. Now, let's look at the example shown in the center of the slide. A researcher wants to determine which factors are associated with academic performance among nursing students. Now, instead of testing one or two carefully selected predictors, the researcher examines 12 different variables. Okay, this include age, BMI, sleep quality, anxiety level, caffeine intake, exercise frequency, diet quality, smartphone use, study hours, social media use, income level, and several others. Now, each variable is analyzed separately using its own statistical test. Now, 11 of the tests produce non-significant results. However, you see here, one variable, exercise frequency, produces a p-value of less than 0.05. Now, the researcher immediately concludes exercise frequency significantly predicts academic performance. But should we accept that conclusion without question? Okay, obviously we shouldn't. This slide also presents an important statistical concept. When there is actually no true association in the population, the probability of obtaining at least one significant result increases as the number of tests increases. So the formula shown here is where alpha is the significance level, and the m is the number of statistical tests. So if the alpha level of 0.05 is if the alpha is equal to 0.05, and we conduct, for instance, in this case, the 12 independent tests, the probability of obtaining at least a false positive result increases to approximately 46%. So in other words, there is nearly a 1 in 2 chance that one of these 12 tests will appear significantly purely because of chance. So I hope you get the idea that if you do multiple testing, you increase the chance of finding a true effect, even though if the effect really isn't there. But because of you increasing the chance of it increases the probability of having a significant result because of chance. So now let's look at the flow diagram. The flow diagram on the right side of the slide. Now it clearly illustrates what happens. First, we conclude more statistical tests. We conduct more statistical tests, and then more tests increase the probability of making a type 1 error. And then that higher probability increases the chance of obtaining a false positive result. Those false positive findings can then lead to or lead researchers to draw misleading conclusions. Ultimately, incorrect conclusions may influence nursing education, clinical practice, or healthcare policy. Now, suppose a nursing researcher examines 12 lifestyle factors associated with academic performance. After performing 12 separate analyses, only exercise frequency is statistically significant. Now, without considering the effects of multiple testing, the researcher might recommend implementing exercise programs, as we've seen in the example here. So, to improve academic performance, the researchers recommend implementing exercise programs, and then even though that statistically significant result may simply be a product of chance rather than a true relationship. So if another researcher repeats the study, most probably the results may completely these results may completely disappear. Now, how do we reduce this threat? The first strategy is to pre-specify, of course, the primary hypothesis before collecting the data. Okay, researchers should identify which analyses are confirmatory and which are exploratory. Second is to limit statistical testing to analyses that are theoretically justified. Avoid testing every available variable simply because the software allows it. Okay, because the software will allow you to will still compute for the p-values as you click on you do your several clicks in the software, and then the software will just simply vomit the p-values for you. But of course, it's up to you to avoid testing every available variable. Apply statistical correlations for multiple comparisons. For example, examples include the Bonferroni correction, the home correction, and the procedures that control for the false discovery rate, such as the Benjamini Hochberg method. And finally, report all analysis, not only statistically significant ones, but of course, selective reporting creates a distorted picture of the evidence. You have to be careful. Okay, this issue is particularly important today because statistical software makes it extremely easy to perform hundreds of analyses in only a few minutes. You just click and then do some clicks, and then The statistical software just gives you the p-values. So researchers can compare many groups, test numerous variables, examine multiple outcomes, and conduct countless subgroup analysis. The danger is that without appropriate corrections, some of these discoveries, somewhat discoveries, are almost guaranteed to occur by chance. So if these findings are published and later used to guide nursing practice, they may lead clinicians, to wrong direction. Now, suppose you analyze 20 different predictors of burnout among nurses. Only one predictor produces a p-value of 0.04. Would you immediately conclude that this variable is truly associated with burnout? Hopefully, okay, your answer is no, because your next question should be how many statistical tests were conducted and was any correction for multiple comparisons applied? Okay, the most important lesson is the more statistical tests we perform, the greater chance of finding a statistically significant result purely by chance. So statistical significance does not automatically mean scientific truth. Researchers must consider the entire analytical strategy, not just individual p-values. Okay. Now, multiple testing usually occurs when researchers perform many planned analysis, but there is an even more problematic situation. Now, instead of following a pre-specified analysis plan, some researchers repeatedly search through their data until they eventually find something significant. This practice, which you have to be very mindful about this practice is known as a fishing expedition or data dredging. Um, Now, let's examine why this practice poses a serious threat to statistical conclusion validity. Okay. Now, previously we learned that performing many statistical tests increase the likelihood of obtaining significant findings simply by chance. But now let's consider an even more serious problem, this one. I suppose a researcher doesn't stop after conducting the planned analysis. Instead, the researcher continues to explore the data set, trying different statistical tests, analyzing different subgroups, removing certain participants, adding new variables, or changing the outcome measures until eventually something becomes statistically significant. The practice is known as fishing expedition, which is sometimes called data dredging or p-hacking, if you've heard of it, p-hacking. Now, I'd like you to imagine how does this work and why is this important or an issue? I'd like to imagine you're fishing or you're fishing in a large lake. If your goal is simply to catch any fish, you'll keep casting your net over and over again until eventually something bites. Now, the longer you keep trying, the greater the chance of you catching something. Fishing expedition in research works in much the same way. Instead of testing a carefully planned hypothesis, now the researcher repeatedly searches through the data until a statistically significant result appears. The problem is that the catch may simply be the result of chance. So fishing expedition refers to the practice of repeatedly analyzing the same data set without pre-specified hypotheses, searching for statistically significant findings after looking at the data. Now, rather than allowing the research question to guide the analysis, the data begin to dictate the research question. This strength threatens statistical conclusion validity because significant findings may reflect random variation rather than true scientific relationships. Notice the definition presented on the slide. The key phrase is searching repeatedly through data until statistically significant findings appear. So this often occurs when researchers have no clearly defined analysis plan before data collection. So instead of doing that, after seeing the data, they begin asking new questions. For example, what if I analyze males and females separately? Or what if I exclude participants older than 60? What if I use another statistical test? What if I categorize age differently? What if I analyze only participants with severe disease? Each additional analysis increases the probability of finding a statistically significant result purely by chance. Um, so imagine an example where a researcher develops a stress management program for nursing students. The original hypothesis is that the program reduces stress. After analyzing the data, the p-value is 0.18, which is not statistically significant. Now, instead of accepting the result, the researcher begins searching for something significant. First, the researcher analyzes only female students, still not significant. And then only first year students, still not significant. Then students with high baseline stress. Now, the p-value becomes 0.04. Now, the researcher reports only this analysis and concludes that intervention is effective. Was that truly original research? Was this truly the original research question? Okay, the significant result was discovered only after repeatedly searching through the data. Now, at first, this may seem harmless. Now, you might ask, why is this a problem? At first, it seems harmless. After all, isn't research about discovering new knowledge? Yes, but there's an important difference between exploratory analysis and confirmatory analysis. Confirmatory research um, begins with hypotheses that are specified before the data are analyzed. Exploratory analysis is useful for generating new hypotheses. So the problem occurs when exploratory findings are presented as though they were originally planned. So this greatly increases the likelihood of false positive findings. Now, in recent years, this issue has become one of the central topics in what researchers call the reproducibility crisis, wherein many published studies reported exciting, statistically significant findings. However, when other researchers attempted to repeat the studies, the results could not be reproduced. So one major reason was the widespread use of data dredging and p-hacking. So today's scientific journals, they increasingly encourage researchers to pre-register their hypotheses and analysis plans before data collection begins. Okay, what are the common forms of data dredging? Fishing expeditions can occur in many ways. So researchers may test dozens of variables until one becomes significant, try multiple statistical tests, and report only one that gives the smallest p-value, report or remove uh, problematic participants without clear justification. They just, with without enough or clear justifications, they remove participants from the data, um, from their data, okay, and then analyze numerous subgroups until one produces significance and change the primary outcomes after seeing the results. Stop collecting data as soon as significance is achieved, and although each action may seem, minor, together they substantially increase the probability of false discoveries. So how can researchers avoid fishing expeditions? The first strategy is obviously to develop statistical analysis plan before collecting the data. Before collecting the data, now specify your hypothesis. What do you really want to prove in your study? Primary outcomes and statistical methods in advance. So second one is to pre-register your study whenever possible, like clinicaltrials.gov, the Open Science Framework, and other registries. Now, they allow researchers to publicly record their plans before data analysis begins. Third is to distinguish clearly between confirmatory and exploratory analysis. Exploratory findings are valuable, but no, they should be described as hypothesis generating rather than definitive evidence. Finally, report all analysis transparently, including those that were not statistically significant. Okay, now at this point, I want you to imagine a hospital, deciding whether to implement a new patient education program based on a published study. If the published findings result from data dredging rather than pre-planned analysis, the hospital may invest considerable time and resources into an intervention that is not actually effective. Okay, this is why transparency in statistical analysis is essential for evidence-based nursing practice. Now, if you notice, uh, what I also would like to emphasize is an important ethical principle. Exploratory analysis are not inherently wrong. In fact, they often lead to important scientific discoveries. The problem arises only when researchers fail to distinguish between findings that were planned beforehand and findings that were discovered after examining the data. So good science values honesty and transparency. Researchers should never feel compelled to find something significant. Sometimes a well-conducted study that finds no statistically significant effect contributes just as much as scientific knowledge as one that does. Okay. So let's now move to the next threat, which is outliers. Okay. In the previous discussion, we learned that researchers themselves can unintentionally introduce error by repeatedly searching for statistically significant findings. Now, let's shift our attention from researcher behavior to the data themselves. Okay, sometimes the problem is not how we analyze the data, but one or two observations within the data set that behave very differently from all the others. So these observations are what we call the outliers. Um, at this point, I'd like everyone to imagine a simple classroom scenario. Suppose I ask 10 students to report how many hours they studied last night. 9 students answer somewhere between 3 and 5 hours. Then one student confidently says, I studied for 27 hours. Okay. Immediately we should become suspicious. Is that value correct? Okay, was it incorrect? What was did the student misunderstand the question? Or is it actually true? Okay, the single unusual value is what statisticians call an outlier. An outlier is an observation that lies an unusually large distance from the rest of the data. It's much higher or much lower than the other observations in the data set. And outliers are not automatically wrong. Sometimes they represent legitimate participants. Other times they result from measurement errors, data entry mistakes, instrument malfunction, or misunderstanding of survey questions. So the important point is that researchers should never ignore them. Now, notice the illustration on the slide. Most observations cluster together. Then there is one point that is located far away from the rest. That single point may appear harmless. However, it has potential to influence many statistical calculations. So, as shown on the slide, outliers can, distort um, the mean. They distort the mean, the standard deviation, correlation coefficients, regression coefficients. In other words, one unusual observation can change the conclusions of an entire study. So, um, are outliers always bad? This is a very important question. Should researchers automatically remove every outlier? The answer is no. An outlier may represent a data entry error, an equipment malfunction, a participant misunderstanding, or a genuinely unusual participant. For example, suppose your study examines blood glucose levels among patients with diabetes. One patient has a glucose level of 520 milligrams per deciliter. Is that necessarily an error? May not be an error at all. It may represent a patient experiencing severe hyperglycemia. Removing that participant simply because the value is extremely or extreme would actually introduce bias. So, therefore, researchers should investigate the outliers first, before deciding whether to retain or exclude them. What are the strategies for managing outliers? So notice that the recommendations shown at the bottom of the slide, we first identify potential outliers. This can be done by using box plots, scatter plots, histograms, standardized z-scores, or residual analysis. Then you investigate their origin. You ask, was this caused by data entry, measurement error, instrument malfunction, or is this a legitimate observation? And then justify any decision to retain or remove an outlier. I'd like to emphasize something that experienced researchers learn very clearly, that outliers are often telling us a story. Sometimes, that's the story is a mistake occurred during data collection, and sometimes the story is, this participant is fundamentally different from the others. Instead of immediately deleting outliers, good researchers, they investigate why are these outliers there in the first place. So sometimes the most interesting scientific discoveries begin with one unexpected observation. Okay, so the key takeaway with this one is that I'd like you to remember that outliers should never be ignored, but they should never be removed without careful investigation and scientific justification. So far we have examined situations where one or two observations are unusually different from everyone else. Our next threat is almost the opposite. Okay. Instead of having too much variability, researchers sometimes have too little variability. Okay. In our previous discussion, we learned that too much variability, particularly because outliers um, can distort our statistical analysis. Now let's examine the opposite. Sometimes researchers don't have too much variation. Instead, they have too little variation. Now, although this may sound like a good thing, it can actually weaken statistical relationships. And this threat is called range restriction. I'd like you to imagine now that you're trying to determine whether height is related to weight. Now, instead of studying people from the entire population, you decide to include only professional basketball players. Will there be much variation in height? Oh, probably not. Most basketball players are already quite tall. So, because everyone is similar, it becomes difficult to observe the true relationship between height and weight. So, this exactly is what range restriction does. Range restriction occurs when the variability of a variable is artificially limited. You decided to limit the range of that variable because participants are too similar to one another. The observed relationship between variables becomes weaker than it truly is. Now, notice the illustration on the slide. Now, the researcher wants to study the relationship between intelligence and academic performance. However, only top performing nursing students are included in the study. So immediately we should recognize a problem. Since everyone already performs at a very high academic level, there is very little variability. Without variability, correlation becomes difficult to detect. And you see, now why does this happen? Correlation depends on variation. So if everyone has nearly identical scores, there is very little information for the statistical test to work with. So as a result, even if intelligence truly influences academic performance, the observed correlation may appear very weak. So the relationship hasn't disappeared. It has simply become difficult to observe because the range has been restricted. Imagine that you want to determine whether clinical competence is associated with self-confidence. Suppose we recruit only graduating nursing students who already passed their comprehensive competency examination. Would we expect much variation in competence? Probably. Oh, we wouldn't. Most students already demonstrate high competence. So, consequently, the observed relationship between competence and confidence may appear much weaker than it actually is in the general nursing student population. So, how can researchers avoid this problem? First, select participants who represent the full range of the population whenever appropriate. You avoid unnecessarily restrictive inclusion criteria. Consider whether your sampling strategy may unintentionally reduce variability, and of course, you always interpret weak correlation carefully when studying highly homogeneous samples. It's time to go to bed. Okay. Now, let's move on to the next threat. So, if range restriction represents too little variation, heterogeneity represents too much variation, which is our next threat. Heterogeneity of the participants. Although diversity is often desirable, excessive variability can make it difficult to detect treatment effects. So imagine that you're testing a new antihypertensive medication. Would you combine children, young adults, middle-aged adults, elderly patients, and critically ill patients into one analysis without considering their differences? No, of course you wouldn't, because these groups differ in many important ways. Those differences may overwhelm the effect of the medication itself. So heterogeneity of participants occurs when excessive variability among participants increases random error and makes true treatment effects. Okay, so notice in the example shown. Okay, the researcher combines adolescents, adults, and elderly participants into one analysis. Age influences physiology, metabolism, cognitive function, health behaviors, and response to treatment. So if age is ignored, its effects become mixed together with the treatment effect. And as a result, the statistical analysis may fail to detect the intervention's true effectiveness. Okay, suppose we evaluate a health education program designed to improve medication adherence. The sample includes teenagers, working adults, older adults. Each group learns differently. Each group has different health benefits, different cognitive abilities, and different levels of health literacy. So, uh, pulling everyone together may substantially increase variability, and consequently, the educational intervention may appear ineffective. So even though it actually works within each age group, um, even though it actually works within each age group. So how do we reduce this stress, this threat? Researchers have several options. They may restrict the sample to a more homogeneous population. You stratify participants according to important characteristics. You match participants, or statistically just adjust for important variables using regression analysis or analysis of
It's 11 o'clock.
covariates. The appropriate strategy depends on the research question. So, one common misconception is that larger samples automatically solve every statistical problem, but not necessarily. A large but extremely heterogeneous sample may still obscure important treatment effects. Good sampling is about obtaining the right participants, not simply the greatest number of participants. So excessive participant variability increases random error and may conceal the true treatment effects. Okay. Now let's move on to the next threat, which is attrition. Now imagine that you begin a clinical trial with 100 participants. Everything seems well planned, but by the end of the study, only 60 participants remain. What happened? Some participants moved away, others became too busy, some withdrew consent, others simply stopped responding. This loss of participants is called attrition. Okay, attrition refers to the loss of participants after a study has begun. Participant dropout reduces sample size, decreases statistical power, and may introduce bias if dropout differs between study groups. Now, notice the participant flow diagram. At the beginning, okay, okay, both groups contain, look at these two groups of nursing students were followed after for 6 months. Participants begin dropping out as the study progresses. Now, if dropout occurs equally in both groups, the effect may primarily be reduced statistical power, but if one group loses substantially more participants than the other, a much more serious problem arises, and this is called differential attrition. Okay. This one is differential attrition. This one is differential attrition. Suppose participants receive the intervention suppose participants receiving the intervention experience unpleasant side effects, mainly withdraw from the study, and the control group experiences very little dropout. The remaining intervention participants may now represent only the healthiest or the most motivated participants or individuals. So comparing these groups is no longer fair because the groups have changed. So that's where the problem occurs with when it comes to differential attrition. So how do we reduce attrition? Researchers should attempt to prevent dropouts whenever possible, like maintaining regular communications, sending reminders, providing flexible appointment schedules, building rapport, reducing participant burden, and offering reasonable incentives when ethically appropriate. Researchers should also carefully document the reasons for participant withdrawal. So when reviewing research articles, don't focus only on how many participants were recruited. You have to also ask how many completed the study, because sometimes a study begins with an excellent sample size but loses nearly half of its participants before the final analysis, and that should immediately raise concerns about statistical conclusion validity. Okay, the key takeaway is that attrition reduces statistical power and may introduce serious bias when participant dropout differs between comparison groups, and that's when uh, what we call differential attrition, wherein significantly there is significantly more dropouts or attrition on one group over the other. Um, So we've now discussed threats related to statistical power measurement, variability, participant characteristics, and participant retention. Now we'll examine another common source of error, which using the wrong statistical test for the data, even when the data collection is excellent. Okay, let's move on to inappropriate statistical tests. So far, those problems that we've discussed related to sample size, participant characteristics, missing data, and variability. Now, let's suppose we've done everything correctly and we have an adequate sample size, participant completed the study, the measurements are reliable, the data have been carefully entered. Does that guarantee valid conclusions? Do you think? Oh, well, of course, not necessarily. One of the most common mistakes is in research occurs during the data analysis itself using the wrong statistical test. Um, what I often tell my students that use SPSS or any statistical software is like, uh, oh, tell my students that uh, is it any statistical software is like a calculator. No, SPSS, for instance, it's like a calculator. A calculator performs whatever calculations you request. That's the idea. So if you ask it to calculate the wrong thing, it will still give you an answer. The software assumes you selected the correct analysis. So therefore, you choosing the appropriate statistical test is the researcher's responsibility. It's not the computer's responsibility. Now, an appropriate statistical test is one that does not match the research question, it doesn't match the research design, doesn't match the type of variables or the levels of measurement. So when researchers select an appropriate statistical procedure, the resulting p-values, confidence intervals, and conclusions may all become invalid. So let's look at the examples presented on the slide. For instance, see Pearson versus Spearman. Pearson versus Spearman. Um, Pearson correlation is designed for continuous variables. Okay, Pearson, this one. This is designed for continuous variables that are approximately normally distributed and have a linear relationship. Suppose that your data is ordinal, for example, Likert scale, ratings of patient satisfaction, 1, 2, 3, 4, 5 for patient satisfaction. Would Pearson correlation be appropriate? Okay. Of course, not, because in Pearson correlation, it has to be an interval data or a scale. So ordinal data violate one of the assumptions of Pearson correlation. A better choice would be or Spearman's rank correlation, which is specifically designed for ordinal or non-normal continuous variable. Selecting the wrong correlation coefficient may produce misleading estimates of the relationship. Another is when we look at multiple t-tests instead of ANOVA. So you have here different or multiple t-tests were conducted instead of using ANOVA. The second example is a mistake, this one. Uh, Suppose we want to compare three teaching methods. Some students perform teaching method A versus B, then A versus C, and then B versus C using three separate independent t-tests. That is, of course, inappropriate. Every additional t-test increases the probability of type 1 error, as we've mentioned in our previous slides on the different threats multiple statistical tests. So we should perform instead a one-way ANOVA or analysis of variance. If the ANOVA is significant, then we conduct appropriate post hoc tests. Now this controls the overall error rate. Another example is this one on cluster data or violation of independence. This example is particularly important in nursing and public health research. Now, Suppose patients come from several hospital wards, and patients within the same ward often resemble one another because they receive similar care, work with the same healthcare team, and follow similar clinical protocols. These observations are not truly independent. If researchers ignore this clustering and analyze all patients as though they were completely independent, standard errors become artificially small. So p-values become misleading, and researchers may incorrectly conclude that interventions are statistically significant. So in these situations, multi-level modeling, mixed effects models, or generalized estimating equations are often more appropriately. What I'd like everyone to remember is one important rule. Every statistical test answers a specific question. The challenge for researchers is selecting the test that matches their research question. So for example, if comparing two independent means, use an independent t-test. For comparing three or more means, use ANOVA. Association between two continuous variables, Pearson correlation, and association involving ordinal variables like you use Likert scale, then Spearman correlation is the appropriate choice. Do you measure association between categorical variables and chi-square? Choosing the correct test begins long before opening the SPSS. If you be using the SPSS or any statistical software that you prefer to use. So statistical power performs calculations correctly, but it cannot decide whether the researcher selected the correct statistical test. So it's up to the researcher. We also have different threats related to statistical conclusion validity, which we have discussed a while back, including data coding and entry errors, wherein incorrect coding produces inaccurate analysis. We've mentioned this a while back in our previous discussions, as well as inflated type 1 and type 2 errors, which we've discussed earlier on during our discussion of different of the uh, you know, first threats to statistical conclusion validity. Now, let's move on to the next slide, which is what we can do now. Now that we have examined the major threats to statistical conclusion validity. Now, the good news is that just like in construct validity, almost all of these threats are preventable through careful planning. So good statistical conclusion validity doesn't begin when you open SPSS or any statistical software. It begins during the planning stage of the research. So the goal of statistical conclusion validity is simple. We want our statistical conclusions to reflect reality. We want the goal of statistical conclusion validity is, to make statistical inferences and sound decisions that truly reflect reality. And we have different recommendations to do, like conducting power analysis, using reliable and valid measurement instruments, choosing statistical tests appropriate, check assumptions before conducting analysis, screen data for missing values, outliers, and coding errors, adjust for multiple comparisons, report effect sizes. We mentioned this a while back, and 95 confident intervals in addition to the p-values. And we pre-register hypothesis and analysis plans and consult, of course, a statistician during the planning phase before you even collect the data. So the key takeaway here is that good research goes beyond collecting data. It requires careful planning, appropriate analysis, and transparent reporting. I also know made here a comparison of the construct validity and statistical conclusion validity. Students often confuse construct validity with statistical conclusion validity because both affect research quality. However, these are two different questions. So, construct validity asks, are we measuring what we intend to measure? Its primary concern is the quality of measurement. Did our questionnaire truly measure stress? Did our intervention truly represent simulation-based education? Did our operational definitions accurately represent our theoretical concepts? If the answer is no, the construct itself is flawed. So, on the other hand, statistical conclusion validity asks, do the data justify the conclusions we are making? Here, the measurement may be perfectly valid, but the researchers might still reach incorrect conclusions because of poor statistical analysis, small samples, assumption violations, or inappropriate statistical tests. I often summarize the difference using two simple questions. Construct validity asks, did we measure the right thing? Statistical conclusion validity asks, did we analyze the data correctly? So one concerns measurement, the other concerns statistical analysis. Typical solutions is that construct validity improves through validated instruments, clear conceptual definitions, and standardized interventions. Statistical conclusion validity improves through adequate sample size, appropriate statistical analysis, data screening, and reporting effect sizes. So, uh, I've mentioned this a while back in a simple analogy wherein you imagine building a house. Construct validity ensures that you are using the correct building materials. Statistical conclusion validity ensures that you assemble those materials correctly. So using excellent materials incorrectly still produces a poor house. Likewise, perfect statistical analysis cannot rescue poorly measured constructs. So which would you rather have? An excellent measurement with poor statistics or excellent statistics with poor measurement? Of course, neither, because high quality research requires both. Construct validity ensures that we measure the correct concepts. Statistical conclusion validity ensures that we analyze those measurements correctly. Both are essential for trustworthy research. Now, this brings us to our final slide. Rather than introducing another concept, I'd like us to reflect on why all of this matters. Throughout this lecture, we discussed many threats, many statistical concepts, and many methodological issues. Some of you may be wondering, will I really use all of this in practice? Of course, the answer is yes. Perhaps not every statistical formula, but certainly the way of thinking. On the left, we see construct validity that this reminds us to ask, are we studying the right concepts? Before collecting any data, we must clearly define our variables, select validated instruments, and ensure that our measures truly represent what we intend to study. On the right, we see statistical conclusion validity, which we ask, are we analyzing the data correctly? So good statistical practice requires appropriate analysis, checking assumptions, adequate statistical power, and honest interpretation of findings. The most important message on this slide appears in the center. Construct validity and statistical conclusion validity are not competing ideas. They work together, and when we measure correctly and analyze correctly, we produce trustworthy evidence. And why is trustworthy evidence important? Because you see, research does not remain inside journals. Research influences they influence clinical practice, they influence patient care, they influence education, health programs, hospital policies, national health guidelines. Poor research can lead to poor decisions. Strong research improves lives. So, whether you become clinical nurses, educators, administrators, or researchers, you will constantly encounter research articles. Your responsibility is not simply to read them, your responsibility is to evaluate them critically. So, ask yourself, were the variables measured appropriately? Were the statistical analysis suitable? Can the conclusions truly be tested? I'd like to leave you one final thought. Evidence-based nursing is built upon evidence, but evidence is only as strong as the methods used to produce it. As future nurses, you are not merely consumers of research, you are future producers of knowledge. The quality of your future research may ultimately influence the quality of patient care delivered to thousands of people. So today, we have learned two very important lessons. First, measure the right thing. That is the essence of construct validity. Second, analyze the data correctly. That is the essence of statistical conclusion validity. When both are present, research findings become trustworthy. Clinical decisions become more evidence based, and patient outcomes ultimately improve. Remember, good research is not about finding significant results, it's about finding the truth. So, uh, thank you, everyone. And I hope this discussion helps you become not only better nursing researchers, but also more critical consumers of scientific evidence.